I want to take a little time and talk about one of my favorite applications of momentum change, and that is the impulse momentum rule. So first off, section 8.2, the third reading assignment includes this, but section 2 is about impulse, and one of the big things about this is where momentum change really relates to real life. So this idea that the change in momentum is equal to the net force the change in momentum of something is equal to the net force acting on that something multiplied by the time over which that force acts. So that's the one equation down here near the bottom of your screen. So that doesn't seem like much, but when you think about it, if you drop something on the ground, so you drop something that's not super breakable, but kind of breakable. So I'm trying to think what that might be. Maybe a snack, a chip. I had a corn chip for lunch. Sometimes you drop a corn chip on the floor, it breaks, sometimes it doesn't. So if you were to drop that corn chip on a hard floor versus on a pillow, you sort of intuitively know you'd rather drop that thing on a pillow, or take something that's definitely breakable, an egg that's not hard-boiled. Drop that hard-boiled egg on a floor versus dropping it on a mattress or a foam pillow. The egg's probably going to survive more likely on the mattress or foam pillow. That's because the change in momentum is the same either case. You drop that egg 1 meter from your hand to the floor, or 1 meter from your hand to a pillow. The change in momentum, it's falling a meter, it's being pulled by the earth, so its velocity just before it hits the ground or the pillow is going to be the same. So m times delta v is going to be the same, because delta v is going to be the same, and the egg doesn't change mass on the way down. But the collision is going to be different. So I want to show you this simulation. It's from a site called the Physics Classroom, Egg Drop Activity. So we can run a bunch of different trials, and here's an egg, small, medium, large egg. We can go with the default here. So small egg, dropped 1 meter onto a hard floor. So we're going to run the trial, and so our small egg, 40 grams, 1 meter, hard floor. Drop the egg. Now you know why I didn't pick something larger, and definitely the egg breaks. So we look at this, we see on impact the velocity change was 4.4 meters per second. This velocity took place over a time of 4/1000ths of a second. So collisions with hard surfaces happen really quickly. So the force here is m times delta v, 0.04 kilograms times 4.4 meters per second, divided by this tiny time interval, so 44 newtons. So the force, the average force acting on that egg is 44 newtons. So we're going to change the conditions here and drop it onto a 1-inch foam. So we still have the same size egg, dropped over the same 1 meter, and we're going to drop it this time. And so we look, same mass, same change in velocity, 4.4 meters per second. But this time the average velocity took place over 4/100ths, not 4/1000ths of a second. So the collision took 10 times as long. The force exerted is just 1/10. So not 44 newtons, but 4.4 newtons. So I'm going to change the conditions again. And I'd like you to just take a minute, and now we're dropping the meter. We're probably raising it up a little bit because that's a pretty thick foam box, but we're dropping it 1 meter. So guess in general what you think the force acting on that egg would be. For sure, is it going to be more than 44 newtons, between 44 and 4.4, or less than 4.4? So again, the change in velocity is 4.4 meters per second, but now the collision took half or twice as long as with just the foam, like the sponge or whatever it was. So the force was half as great. Think about the applications of this. Going from a certain speed, so let's say you're going 65 miles per hour and you're on the highway, you slide on some ice and you hit a retaining wall. Imagine you don't have your seatbelt on and you collide with the steering wheel. You're going to hit the steering wheel, and depending on how much body fat you have, you're going to compress a little bit, but probably not very much. So when you hit the steering wheel, that collision is really quick. Or your passenger who didn't wear their seatbelt, they collide with the dashboard, or worse, the windshield, that collision is going to be really quick. So the momentum changes are going to be the same. You're going from 65 miles per hour to 0 miles per hour, and you're whatever, 60 kilogram mass. So that's the same change in momentum. But if the collision takes a very short time, a very small amount of time, then in this formula here, delta T is small, which means the net force has to be large. If you have your seatbelt on, or if you hit an airbag, the airbag extends the time of that collision by a factor of a lot. An airbag probably by a factor of 10 or more. Seatbelt, not quite as much. But if the collision is extended by a time factor of 10 or more, the force is going to be just 1/10 as great. If you'd like to try this out yourself, or you've got a niece or a nephew who thinks physics is fun, this physicsclassroom.com website is a great website for you to visit.